because I think Yanji, the like keep moving the problem sets, so because I think they were all.
Okay. Let's get going. That everybody's here. So as usual. Why is it like this?
Maybe the universe doesn't want you to see it today.
Did the solar eclipse happen early? Oh, okay.
It doesn't work. Oh, yeah. Oh, shit. Oh, wait. Sorry,
Monday.
Okay, that's better. Thank you. So as usual, gotta say this, because Columbia makes me say it. But today is one of these days where I would also like to clarify so today we're going to be talking about our package called brms, Bayesian Regression Models, with Stan, and because it's with Stan and because I'm with Stan and with Columbia and all this. But these sorts of disclosures can make it seem as if I had something to do with BRMS, which I did not. BRMS, 97% of it or something like that, was created by someone named Paul Berkner when he was a PhD student in psychology, not at Columbia. And he did almost everything in the BRMS package, which we're going to be talking about today and next week, and maybe some a little bit the week after that. So I'm teaching it because it's awesome, but that doesn't mean that I deserve any credit for it. Although Paul would say, well, without Stan, there would be no Bayesian regression models with Stan, and that is true, I guess. But this is Paul's thing. But before we talk about that, since today is a holiday, I want to continue with where we left off with last time. So did anyone go to Data Science Day 2024? Oh, yes. You went all day?
No, just a part of it.
Just for part of it?
Neutral.
The Bayesian part of it?
They actually, one of the, I forgot exactly what the presentation was about, but he kept saying friars, and I just kept thinking about Bayesian, but I think he used Bayesian for his analysis. But
So something happened before something else.
Pretty much. Yeah, I don't know. He was also from the stats department, so maybe is he referring to Bayesian? Never explicitly said it, but.
Well, if it's Columbia Stat Department, Columbia, ironically speaking, is one of the least Bayesian stat departments that you can find. So, I don't know. Could have gone either way. I wasn't there. But, wait, you had a...
Oh, I do remember what it's about. It was about like image recovery, so maybe Bayesian wouldn't be applicable to it, but I don't know.
I'm sure it would be applicable, but if there was no discussion of the posterior distribution, then you can be reasonably sure does not overlap with what this class is about. So what did happen at Data Science Day 2024? Those of you who went. Yes.
Yes. There was like I wasn't there for the beginning of this, but they had like a lot of different talks on like they brought like someone from Google to like speak about some of the. He's like the senior vice president of like does like analytics stuff. I forgot what exactly, and then they had like different sessions on like sustainability and then the computer vision, and then there was like an earlier session on algorithms, but. And then afterwards there was a poster session, and there were like actually quite a bit of posters on Bayesian methods, but a lot of them were kind of used on like genomic expression and bio-related stuff, which I can't really grapple my head, so I kind of just like went past those. I'm like, Bayesian methods, cool, but the bio stuff a little bit hard for me to get through, but yeah.
So there were some number, not a huge number, of posters using Bayesian methods. Probably, as far as I could tell, at most one of them was about like the actual methodology, as opposed to like someone's doing a thesis somewhere and they use some sort of Bayesian method or what they refer to as a Bayesian method to obtain estimates, you know, in the field of like testing for hereditary diseases or something like that. I think there was one on so-called Bayesian tempering, which it's like what we've done in the class, except the likelihood function is raised to some power alpha, where alpha is a number between 0 and 1, or equivalent to multiplying the log likelihood by some number between 0 and 1, and thus downweighting it relative to the prior density. You could do that with Stan. Since alpha does not actually appear in Bayes' rule, it's a bit debatable as to why you would want to do that, but there are people who do, because it makes the resulting draws less sensitive to incorrect assumptions about the likelihood function. But anyway, so there certainly are applications of Bayesian stuff in data science, and I'm sure with the various talks that were given, not only at Data Science Day 2024, but Data Science Day in all the previous years where Data Science Day has been recognized, a lot of talk about how data science has to be the intersection of all these different things, and why the Data Science Institute has to exist as a separate thing with separate funding, because what data science is can't be encapsulated within one department. And data science requires collaboration across people with different sorts of educational backgrounds and all this sort of stuff. But nevertheless, I think the point that I was trying to make last week remains, which is that since 1990, at the very latest, Bayesian inference has been at the intersection of all of these things and was, you know, thriving, at least outside of the social sciences, for about 20 years before the term data science was coined, and about 25 years before the Data Science Institute was created at Columbia, and similar institutes are created at virtually every other university. And by and large, instead of building on 25 years of Bayesian inference being at the intersection of this, they largely decided to do their own thing. And their own thing, I would say, does not squarely even hit the center of the intersection that Conway and many other people talk about when they talk about data science. Because, you know, if that was truly their priority, they could have just stuck with Bayesian inference for the most part. Did you have something you wanted to add? So there's certainly going to be, I would say, more emphasis within data science on what's in red here, hacking skills, use of computer, etc. The master's program in data science at Columbia actually does require a quarter-long course on probability and statistics. Not every university actually even has that requirement, but the one at Columbia does, and that's a good thing. A quarter of a class is not really, well, a quarter of a year is not really enough. I mean, they know about as much as about probability as you do. But that's all they really feel they can afford within the required curriculum. Because they have a whole lot of other classes, mostly in this area, that they're required to take that are more what you would usually see in computer science. And they also learn about like how databases work and other stuff like that. But I would say the master's program in data science does not have very much emphasis at all and no required coursework to speak of in the blue area here. And so you get a lot of, you know, people who graduate from that and also, you know, data science day or whatever, but that sort of tilts to more around here. Yes.
A question, what is danger zone exactly?
Well, that's what Conway thinks is a recipe for bad research. So people who have some substantive expertise and they know how to operate a computer, but they're not constrained by probability or statistics. They don't know much about that. And so they can do a whole bunch of regressions, but can't really do anything useful with those because they don't understand what probability means. And then over here, traditional research, which is sort of the intersection of math and statistics knowledge, and having, you know, substantive expertise. You know, you might think of that as like older social scientists who had at one point, you know, courses on this or have spent a whole lot of time studying a particular thing, but they can't really do much by themselves because they don't have the computer skills to get the data and get it in a clean format and so you can analyze it, etc. And at best have to rely on research assistants who have that sort of training to help them more. So any other thoughts on Data Science Day 2024 and its relationship to Bayesian inference?
You mean lack thereof?
Or lack thereof. And speaking of lack thereof, I would be remiss if I did not point out that the 8th edition of Jeff Woolridge's textbook is dropping at midnight tonight. So you can pay $300 for that and see if he's added anything about Bayesian inference or why he does not feel as if Bayesian stuff should be included in his textbook. Like I say, in the previous 7 editions, the word Bayesian does not appear in any of the 800 some odd pages. But he has said a lot, not a lot. There have been a lot of tweets, with not a lot of words, that I would have linked to, except Elon Musk in his infinite wisdom has made it impossible to link to previous Twitter threads unless you pay Twitter to subscribe, which I'm not going to require you to do. So instead of doing that, let's speculate as to why Wooldridge would not include any stuff about Bayesian inference in an introductory econometrics textbook. So what would the case be for not including Bayesian stuff in an introductory econometrics textbook and not making the case for not making the case?
And he believes his audience doesn't have the probability knowledge to grasp it. Although that doesn't make much sense though, because he does have a whole, at least his appendix has it.
Does have an appendix on probability, and probability is used in frequentist stuff, although you can get quite far in a frequentist direction with only the normal distribution, because the sampling distribution of almost every estimator that's used in econometrics is asymptotically normal. So maybe there's a little bit less presumption of probability, and that book is used at the undergraduate level in econ for econ majors who presumably don't have that extensive knowledge of probability. So yeah, I think that's part of it. Wouldn't really justify, or if that was all there was, wouldn't really justify completely omitting it from all 853 pages or whatever, or just say, there's some more advanced stuff out there that requires more in-depth knowledge of probability, and that includes Bayesian stuff that you might, think about taking after this course. So if that was all that was, I think, you could mention it. So that's probably not the only thing on Wooldridge's mind. What else could it possibly be? Well, despite being 853 pages, it is ostensibly an introductory econometrics textbook. And since econometrics is like 2% Bayesian, 98% anti-Bayesian, it's plausible to argue that people who read the introductory econometrics textbook should be exposed to the main things that an econometrician needs to know. And if that's just very small percentage Bayesian and some other things, then, maybe that shouldn't be included. Yes?
I was gonna add onto this, because I remember like the diagram that you kind of showed us with all the different social science subjects. I mean, it's still kind of fairly low of Bayesian methods being used even in economics. So I was thinking like it's still like maybe like it's used in research, but when we're talking about it in an academic setting, like in a textbook, it's not really as like taught as much or like not even thought about in including it. And then I just go back to like introductory methods, like what's been common, what has been like kind of in the field for like such a long time. Kind of going back with the traditional research side of things.
Yeah. So I think it would be just a factual point to say Bayesian stuff is so rare in economics that it doesn't merit inclusion in an introductory econometrics book. The flip side of that is, well, it's not really a sufficient argument to say, okay, we're going to teach what's been taught before if what's been taught before is like not right. I think over the course of the first however many weeks, I guess 11 or something like that, that we've done, made a pretty credible case that all the things that seem backward about frequentist inference, like you don't have to do it that way. You can do it the non-backward way. So that's kind of one fundamental point. And another fundamental point related to that is that Bayesian methods tell you how to update your beliefs about, you know, parameters or predictions about the future or whatever. And conversely, anti-Bayesian methods don't tell you what to believe. So you can get point estimate, you can derive the distribution of the point estimator across all the possible samples from a population, etc. But if the output of the quantitative method is not a probability distribution, then it is not telling you what you should believe if your beliefs are probability distributions. And so, I mean, there's a lot that could be said about these things, but in terms of making just sort of simple points, you know, I think there's a credible case to be made for why the Bayesian stuff is right and the anti-Bayesian stuff is wrong, particularly as applied to social science. In addition, this sort of does not deal with the fact that perhaps the main reason why Bayesian methods are so rare in econometrics is because introductory textbooks don't cover them. If they did, they would presumably be more prevalent. And some other introductory textbooks do have, like, at most a chapter or something on Bayesian stuff. Bill Green's textbook does. The textbook that we use in the political science class in the fall has a chapter. We didn't read it. That's by Hansen. Anyway, so yeah, there's kind of a chicken and egg aspect to this of it. Well, we don't include very much about Bayesian methods in introductory textbooks because econometricians don't use it, but the next generation of econometricians doesn't use it because they haven't learned it because the textbooks didn't cover it. Yes?
I know we had talked about in the first class how game theory is kind of right for Bayesian analysis, but at least to my memory, like when I took game theory my senior year of undergrad, I don't think our textbook mentioned Bayesian once. So,
yes, that is also not, well, didn't talk about perfect Bayesian equilibria.
I don't think so. At least we didn't cover it.
Maybe in an undergraduate class, perhaps not.
Oh.
Perfect Bayesian equilibria is definitely a thing. And the use of probability in game theory definitely is. But the use of the Bayesian stuff in estimators is considerably less prevalent than in theoretical papers coming out of econ. But anyway, all of that I don't think is the primary reason. Oh, yes.
So I think they don't want to update their beliefs about Bayesian stuff and statistics. They don't want to learn more about Bayesian.
They don't want to learn, or the people who write textbooks don't want the students to learn.
Both of them. I think they don't want to update their beliefs about Bayesian, and also they don't want to maybe to students to don't update their beliefs about it.
That's possible. So I think the main thing that Wooldridge has said on Twitter is that Bayesian methods and, by the same token, maximum likelihood make excessively strong assumptions about the distribution of the data. And both maximum likelihood estimator and Bayesian posterior distribution estimator are unnecessarily sensitive to assumptions such as the errors are normally distributed with expectation 0 and standard deviation sigma, and they're independent of all the predictors. So those are the sorts of assumptions that are made in both maximum likelihood and in Bayesian stuff, which uses the likelihood function along with the priors. And it is possible, quite possible, and has been done for decades in econometrics, in contrast to the sort of development of estimators in statistics, to derive estimators where the distribution of the estimator is known to be asymptotically normal, even if, you know, the errors aren't Gaussian, or even if they don't all have the same variance, or even if they're not independent of each other. These sorts of ways of relaxing the distributional assumption about the data generating process. So whereas, you know, we have and will do stuff that says like the errors are, you know, normal or whatever. What is more prized in a lot of stuff with econometrics is to say the errors come from some distribution whose mean is 0 and has some finite standard deviation, but we're not going to say what that distribution is. We're just going to say that it has like 2 or 4 or 12 or whatever finite moments to it. And under those, which is implied if we were to assume the whole thing is Gaussian, but doesn't require like the whole thing to be Gaussian in order for that to be. And then you can derive the distribution of the generalized method of moments estimator or whatever across all possible samples of size n that could be drawn from that population, at least as n goes to infinity. So Hansen, which I was just mentioning earlier, is fairly explicit about that. Wooldridge has been on Twitter. That is, you know, their main, and a lot of microeconometricians kind of make that same argument. So that is, I think, the main reason why you know, people like Wooldridge don't like likelihoods or anything that uses likelihoods because they make an assumption that can be weakened. Now, you know, we've done a whole lot of stuff with like normal errors and stuff like that, and I've tried to emphasize at the time, you don't have to assume this. You can assume other stuff beyond this. But you do have to assume parametric distributions for stuff in order to do Bayesian inference, or more specifically, to get a posterior distribution. You have to be working with input distributions, not like the errors come from some distribution that I'm not going to say what it is, but it has a mean and a variance, or you know, something like that. So in that sense, that is kind of a fundamental difference of opinion as to how social science should proceed. You know, a lot of microeconometricians favor making or weakening the assumptions on the estimator as much as possible. Bayesians, on the other hand, will say, well, okay, we're making stronger assumptions about the data generated process in order to get a posterior distribution as opposed to merely a point estimator. Like, we're not making stronger assumptions just for fun. It's in order to update our beliefs. We have to be working with proper, like, well-defined probability distributions. And we do that in order to answer the question, what should I believe about this data generating process after having conditioned on the data? Which all this stuff from econometrics, even if you weaken down the assumption about, you know, the distribution of the errors and the independence thereof, or all sorts of things like that, doesn't tell you. So these sorts of econometrics books, I think, don't explicitly address and sort of leave it open to the interpretation of the user. Like, what should you believe after doing some generalized method of moment estimator for the parameters? Like, point estimation econometrics can't answer the question, what should you believe? Because it doesn't output a distribution of beliefs. So they just sort of omit the fact that they can't tell you what to believe after, you know, you do the analysis and say, well, it's up to you what to believe. But that sort of opens up the floodgates to not a particularly productive social science literature that isn't being, you know, constrained by the rules of probability the way we've been developing. So anyway, that is a little bit more about that aspect of it, which, no, I don't think will be reflected in the 8th edition of the book. Other questions or thoughts about that? Okay. So another important thing from last time that I didn't have enough time to get into. So this is an example. I just sort of cooked it up with simulated data, but it's representative of a more general phenomenon. So this is for logit models, so binary outcome, no intercept, in order to just have one parameter space, so one predictor, and we have one unknown coefficient to estimate. So the likelihood function is in red here. And consequently, the value of beta that maximizes the likelihood is going to be like 1.75 or somewhere around there. So over here, and then down there. That is the maximum likelihood estimator. Maximum likelihood could legitimately be called maximum overfitting. It yields the value of the parameter or parameters such that the most likely data set to be randomly sampled is the data set that was ostensibly randomly sampled. And so the fit here, or the fit implied by this value of the coefficient, is going to be highest for the present data set, and any other data set that could be sampled from that population is going to be expected to have worse fit than the data set that was used to obtain this maximum likelihood estimator, even if the subsequent data set is sampled from the same population that this data set was. And so, as a widely held but incorrect belief that maximum likelihood estimators produce the most likely estimates of the parameters, which is exactly backwards, like everything with frequency is. The maximum likelihood estimator is the estimator such that the most likely data set to observe is the data set which was observed, assuming it to be randomly sampled from a population. So it isn't called maximum overfitting, but if it was called maximum overfitting, that would be a perfectly adequate description of what maximum likelihood does. And people like Fisher, for the most part, did not care about how well or poorly statistical estimators such as maximum likelihood were at predicting future data. That just wasn't really part of their goal for statistical inference. The main thing that Fisher was interested in doing was estimating treatment effects of agricultural interventions, not it like predicting the amount of rainfall or something like that next year. You know, more interested if we like change the fertilizer or whatever, how does that affect the growth of plants? And so, particularly interested in estimating treatment effects. Later, honestly, they got this obsession about testing and rejecting null hypotheses, but almost never during the heyday of frequentist stuff was anyone really concerned about using models to predict future observables. And so they really didn't care, or they probably didn't recognize, but if they did, they didn't much care, that maximum likelihood yielded maximum overfitting and much worse predictions of future data than past data, because that just wasn't their priority. As long as the estimator was, you know, consistent for the parameters, as long as we could use it to make confidence intervals, test null hypotheses, all of that goes through without even raising the question of how well does the model predict future data. So anyway, we get our maximum overfitting estimator here. And then, you know, starting more or less 2000, there became more interest in supervised learning, where they sort of dispensed with the hypothesis testing and the confidence intervals and weren't necessarily too concerned about estimating treatment effects, but were really interested in how well a model predicts future data. And if you have a maximum overfitting estimator, then it's not going to predict future data very well, or it's going to predict past data much better than it predicts future data. But predicting past data is not very useful, particularly in like a business context. So supervised learning people said, well, what can we do to mitigate the overfitting problem and yield better predictions for future data? And part of the solution that they came up with is, well, we should add a penalization term to the log likelihood, or usually they do the negative log likelihood and then minimize it, but it comes out to be the same. So this, like I said, the lasso penalization or L1 regularization is proportional to the logarithm of a Laplace distribution. And in log form, which this scale is in log form, it has this black shape to it with straight lines coming out either way of 0 because of the absolute value business, and that makes it not differentiable at 0, which then makes it possible that the optimum could be exactly 0. And so the lasso people, they take the regular log likelihood function, they add the L1 regularization, which is equivalent basically to Laplace prior, in order to shift the maximum over from the maximum overfitting to something that would be closer to zero, maybe exactly zero, but maybe just closer to zero, and thereby obtain less overfitting, better predictions of future data. And as we said last time, if you apply a Laplace prior and this likelihood here, then the numerator of Bayes' rule is equivalent to what Lasso is finding the optimum of. And so that's given in blue here, and the optimum occurs in this case exactly at zero. So Lasso has the capacity to yield an optimum where some, or in this case all, of the coefficients are exactly zero, which is essentially to say this predictor is kicked out of the model, or you can leave it in and it gets multiplied by zero and doesn't do anything. And the supervised learning people have convincingly shown over the decades that adding a regularization term to the log likelihood or whatever tends to yield better predictions. And that is because it mitigates the overfitting problem some. So kind of the first core principle of supervised learning is to add penalty functions to shift the optimum over, away from the maximum overfitting optimum to something that's closer to zero. And you'll tend to get better predictions of future data that way. The other core thing about supervised learning is to split your data into a training subset and a testing subset, and sometimes there's also a validation subset, and then sometimes they subset the training subset to do K1 or K-fold cross-validation, choose fitting parameter. Anyway, there's subsetting, lots of subsetting. That can be either random or deterministic. Maybe it makes a difference, but let's not get too caught up on that distinction. The main thing is that you should have some data that is held out of the optimization process. So you only do, find the optimum business, which in this case here, on a subset of your data. And then you use that same subset with various models that you're considering, get the optimum for each of those, and then for each of those models predict the outcomes in the testing data, maybe classification if the outcomes are binary, and then see which procedure or model that you've used yields the best predictions in the testing data at the optimal parameters that were found in the training data for that model. And this often involves a comparison of many, many candidate models. And so the McElrath reading for last time, goes into the idea of, overfitting is kind of the most common and, dangerous problem that people have never heard of. And says other things like that. Richard is not particularly interested in clicks. So he's not inclined to explicitly make the point that he's sort of implicitly making or suggesting in the readings or whatever, because I think he fundamentally doesn't feel like it's worth his time, engaging with a whole lot of back and forth with, people who, don't favor Bayesian analysis or the sorts of studies talking about in this book. So that leaves it to me to sort of make McElry's point more explicit. And so this idea of, overfitting, and particularly the idea of splitting your data into training and testing. Apurva did a great video about this recitation yesterday that if you haven't seen, it's on Canvas already. So anyway, overfitting, splitting your data into training and testing, etc. So that is something that is, or this idea that you have to split your data into training and testing and only use the training data for the estimation part of it and then use the testing data to compare different models to see which one is best at predicting future data and whatnot. And so the idea that by splitting into training and testing, you can combat or mitigate this phenomenon of overfitting. It's slightly true, but mostly bullshit. And I think McElry's focused more on the slightly true aspect of it and the fact that Bayesians need to be somewhat concerned about it without explicitly mentioning the mostly bullshit aspect to it. Not that McElry's is bullshitting you, but the people who insist on splitting your data into training and testing are bullshitting you. And that is stuff that you will learn or have learned in your other classes. That you absolutely have to do this. And the reason why it is mostly bullshit is because the people who are pushing this are failing to acknowledge that the primary reason for overfitting is the use of numerical optimization. So this is easiest to see in the maximum likelihood case. So you find the optimum over here, you get maximum overfitting. And if you penalize it based on how far it's zero, maybe you get less overfitting. But the primary cause of overfitting is using numerical optimization in the first place. If you optimize the red curve to here and then evaluate the fit only at this point, you're doing it at the least representative point in the entire parameter space. You're evaluating the fit at the point where the fit is absolutely the highest on the data that you use to obtain the maximum likelihood estimate. What Bayesians do is evaluate the fit not at any one point, but evaluate the fit over the entire blue curve. This, if it was not in log scale, the blue curve would have an area of 1 underneath. And so rather than evaluating the fit at the most naively optimistic point in the entire sample space, Bayesians evaluate the fit at every point in the parameter space, weighted by the posterior density, and obtain expected or average fit rather than fit at the mode, which is basically what supervised learning does. They just shift the mode over. So in a Bayesian analysis, the average fit, represented by ELPD, should not be substantially higher or lower or different in the data that you conditioned on than in future data. The fit at the mode definitely will be, because the mode is excessively sensitive to the idiosyncrasies of the data that you have already. But like I've said repeatedly, the mode is not that important to Bayesians. The median or the mean are much more interesting quantities. And that's why we compute the expectation of log predictive density of future data using a leave one out concept estimator that we talked about last time. But anyway, it's an estimator of average fit, not best case scenario fit. So it's the best case scenario business that is the primary reason for overfitting. And just by doing not numerical optimization, but sampling, you have the capacity to avoid the problem, or really the problem didn't exist in the first place. The problem was only created by you doing the evaluation only at the mode instead of averaging over 4,000 draws or whatever from this posterior distribution. Now, Bayesians can overfit the data that they conditioned on. That is usually going to result in situations when your priors are way too weak. So then the influence of the data, including all its idiosyncrasies, is, too strong. You can get into a situation where you're overfit. It's rather easily corrected by using like real priors and checking the prior predictive distribution is reasonable before you start. So it's a fairly easily avoidable problem, even if it's possible to have the problem. Moreover, when you do posterior predictive checks and evaluate the Pareto K and stuff like that, you should also recognize whether you have a overfitting problem. So, although it's true that Bayesians can overfit, they shouldn't overfit without realizing they're overfitting. And if that's like a major issue, changing the model to make it better. But you will find a lot of people who say, well, you have to split your data into training and testing. And that is actively harmful in addition to being wrong in a Bayesian analysis. Because if you held out 20% or more or whatever of your data, then you're not conditioning on that. And your posterior distribution is going to be more dispersed because you're not feeding it all the information from all the data that you've collected. And if your posterior distribution is more spread out, then the predictions implied by the posterior distribution, aka the posterior predictive distribution, are going to be more spread out. And your predictions of future data are going to be worse because you didn't condition on all the data from the past that you collected. Now, supervised learning people say, well, that's the price you have to pay in order to have a clean testing set in order to evaluate which models are best and all that stuff. And that is wrong from a Bayesian perspective because we can do all the model comparison stuff that we need to do using the data that we've already conditioned on. And so there's no reason why we should not use all the data that we've had to get the best possible posterior distribution and thereby the best possible posterior predictive distribution, because all this stuff about model comparison, model averaging or whatever, we can do with leave one out cross-validation concepts instead of leaving out a whole bunch of data. But you will definitely encounter people who think you're naive by not splitting your data into training and testing, when really the opposite is true. Right? Questions about that? And it's really a fundamental thing in terms of we want to evaluate model fit, model comparison based on averages. And people who produce point estimates have nothing to average over. So there's no distribution there. So they have to do, penalization and downsampling and early stopping and all kinds of other stuff to mitigate a problem that they created for themselves by using point estimation rather than distribution estimation. The problem mostly doesn't exist. And if it does exist, you should be able to detect it if you use posterior distribution and average your fit measure over your uncertainty about the parameters, which is the scientifically responsible thing to do in the first place, instead of merely pretending all that uncertainty about the parameters doesn't exist, which is what point estimation does. Okay, so now let's talk about BRMS. So this appears in the reading, this like workflow thing. So what does BRMS do? Well, the user, that's you, is going to pass all the model information to the BRM function in the BRMS package. BRM internally calls two functions which are exposed, so you could call them yourself and look at them. It's not going to be required for anything this semester, but BRM calls two functions, make stand code and make stand data. And so fundamentally what BRMS is doing is taking our syntax, translating it into the equivalent stand syntax, and then all of that is going to get passed to functions in RSTAN, and particularly the MCMC sampling function. RSTAN, when you call it with stand code that has been generated, is going to have to translate that to C++, so it can be compiled. That's why you need a C++ toolchain to do this stuff we're going to do today. And then it's fitted, or you draw from the posterior distribution using the algorithm in STAN that we've been talking about. Then, you know, the 4,000 or whatever draws come back to BRM, which can do some post-processing stuff, making plots and all sorts of things like that. And then the results of all this can be investigated using various R methods defined on the objects produced by BRM. And so how does this differ from what RSTAN-ARM has? Well, the STAN programs in RSTAN-ARM are written by hand. And they are compiled on the CRAN servers. So you can just download RSTAN-ARM and you don't have to compile anything new. But those STAN programs that are written by hand and compiled on the CRAN servers, they're basically just, you know, whatever they are at the time the package got uploaded. There's 6 or 7 of them, and they have a lot of functionality to it. But if you can make the STAN code for a particular model at runtime, then that gives you a whole lot more flexibility in terms of the various different models that can be drawn from their parameters from the posterior distribution using the algorithms in STAN. So this sort of does the translation from R syntax to STAN syntax, and then from STAN syntax to C++ at runtime. And so it has much higher capacity for customization in the different models that you can do. And I haven't counted it exactly, but my strong suspicion is that just with what's in BRMS, it probably can do more models than Stata because of this tremendous flexibility. So what are the arguments to the BRM function? There are many, but the main ones are in the top line here. Formula that implies the linear predictor, data frame where all the variables are, the family, which is essentially the likelihood function, and some specification for the priors. All this other stuff is rarely used, and a lot of it has defaults, which are the same as the defaults in RSTAN, which you ordinarily would not need to fiddle with. And these first 3 here are pretty much the same as in R stand arm, and they're pretty much the same as in, frequentist packages and stuff in R. The thing about the prior is a little bit different in its syntax, but conceptually speaking, it's the same. You have to specify some prior about the parameters in order to do Bayesian analysis. So anyway, most of the action is in these first four arguments here, and these first four arguments are not really that big a deal, or shouldn't be too unfamiliar to you. So with the formula argument, it's pretty much the same as in the rest of R. In particular, the right-hand side of the tilde is really the same. The thing to the left of the tilde is often just the outcome, but BRM introduces a few additional possibilities for a syntax which is like outcome variable, vertical bar, and then some other thing, which is, some of them are listed here. So if you had censored outcome or truncated outcome, you could specify where the truncation starts. There's some stuff about weights, which is really more frequentist, so we're not even going to talk about it. There's another thing where you can specify standard errors on the outcome. This is useful in a number of things like meta-analysis, where you might be modeling like the point estimates in the literature, and then the point estimates all have associated standard errors with them and stuff like that. Probably the one that is the most useful is trials. So if you need to specify a binomial model, so y would be the number of successes, and the variable that you put in trials is the size or the number of opportunities for success. You can also specify categorical models with the cat thing, where that may have more categories than are actually reflected in your outcome variables. So there might be like 10 possible outcome categories, but you only observe 9 of them in the data. You can specify all 10 categories in order to reflect the fact the population maybe. But anyway, bottom line, the formula is mostly the same as other formulas are in R. Also very similar, although there are many more possibilities, the family argument to BRM. These are all the ones, the last time I compiled this list, of essentially likelihood functions that could be used in a call to BRM. But each of these functions has like 5 or 6 possibilities for what the link function could be. So we've got Bernoulli, which is actually just a special case of binomial, but in BRM, those could be separate. So you got like Bernoulli family, but you could have Bernoulli family with a logit link function, or Bernoulli family with a probit link function, or some other things like this. And so basically all of these are going to have a few different choices for what the link function would be under a model like that. And there's, a whole bunch of different likelihood families here, so you could use them. All right, so the main difference between BRM and like Stan GLM and stuff like that is the syntax in which the prior is specified. So there's both a set prior function, which requires stuff to be strings, which is kind of annoying, and then a prior function, which doesn't require stuff to be included in strings, and it just stringifies everything and calls set prior. So for some reason, typing out the quotation marks is really annoying. And so I usually just call the prior function. And you need to specify these things in the syntax of the Stan language, which, as I said before, we're not explicitly learning. But you do need to sort of learn enough in order to specify priors. The class argument pertains to, okay, which parameters are we specifying the prior to pertain to? So B is the default. That means the regression coefficients. you can have a different prior on the first regression coefficient and the second. They can even be from different families. But to do that, you need to specify the class argument to indicate which variable you're talking about when you're specifying this. And then some other things we may see later when we get into hierarchical models and parameters with lower bounds and upper bounds and things like that. But basically, most of the thing involves prior, which is a distribution such as normal 0, 5. What does that pertain to? And then within it, which parameter within that class. And so perhaps this would be easier with an example. So if you call the get prior function in brms with like the formula, the data frame, and the family of the likelihood that you're going to use, it comes back with this data frame of information saying what the default prior choices would be, which you should definitely familiarize yourself with before proceeding. But in most cases, particularly in this class, you should not actually use the default prior choices because they're not that great, but they couldn't be that great because Paul didn't know what your data or your model was about. So how could he possibly choose a better prior than you, who should know that sort of thing? But along that point, the default prior on regression coefficients in BRMS is said flat, which is sort of a euphemism for improper, which is the sort of prior I said you should not use because it does not integrate to 1 over the entire real line. But nonetheless, it is the default prior for class B parameters, which is the coefficients. And in this case, there is one parameter, which is the coefficient on X in the Oken's law. So if I did BRM with the default priors, it runs, but it assumes this improper prior on the coefficient when anyone with passing familiarity with macroeconomic data knows that you can't have too huge a coefficient. Here, it's not the case that all values of the parameter are equally plausible a priori. It should be slightly positive, but it can't be too bad, or slightly negative the way it's written here. Anyway, there's also a prior by default on the intercept. So this is a proper prior, uses a student t with 3 degrees of freedom and a scale of 2.5. So that is proper. It's still terrible in this context. So a student t with 3 degrees of freedom is going to have extraordinarily heavy tails, when really you should have fairly concentrated prior beliefs about the intercept in the Oken's law situation. Like R-stan-arm, BRMS by default is going to center all the predictors internally. Consequently, the intercept pertains to the expected outcome when the predictor is average rather than when the predictor is 0. But you should have beliefs that are stronger than student t with 3 degrees of freedom about the average quarterly value of GDO when the change in unemployment is average, which on average it's 0. So this is proper but excessively weak. Also, there's a prior on sigma, the standard deviation of the errors, which by default is half student t with 3 degrees of freedom, which is also probably going to have an excessively heavy right tail in this context. But because, when BRMS doesn't know what GDO or X or your model means, it's not really it doesn't have the capacity to make like intelligent recommendations as to what your priors are, but it has to have something there for the defaults for the large number of people who just don't want to think about any of this, like they just wanted to run and get back numbers. And it also should be said that Paul's PhD was in psychology and is mostly writing BRMS for a psychology audience, and that psychology audience has 0 to negative amounts of training in Bayesian stuff. So there's a lot of usage of BRMS with improper priors by people who don't want to think about what the priors should be, not that they affirmatively think that these default priors are good. So the way in which you sort of specify this in BRMS syntax is you call prior and you sort of specify the distribution you want, you indicate what it pertains to, and then you plus them together. So that doesn't mean addition, it means like glue. So if I glue these 3 things together, now I have a prior over the 3 parameters in the Oken's law model. And now I can call BRM and pass this thing to it in order to make it go. Okay? So I'm going to have a prior with expectation -2 and standard deviation of 1 on the coefficient for unemployment rate, a prior with expectation of 3 and a standard deviation of ½ on the intercept, the expectation of GDO when x is 0, and prior with a mean of 2 with an exponential distribution for sigma. So these are similar or the same as the priors I've used with RStan ARM when doing this with Stan GLM. Just a little bit of a different syntax in how that information is conveyed to BRM as opposed to how it's conveyed to Stan GLM. As with everything with Stan, usually it's good to use all the cores that you have. So specify the formula, the data frame where the variables are, the likelihood function. So in this case, we're assuming it to be Gaussian, independent, all that stuff that Wooldridge doesn't like. Specify prior, the thing on the previous slide, and you get back quickly, well, a little bit less quickly because it has to compile the C++, but once it's compiled, you get back quickly these draws from the posterior distribution. The default print output looks a little bit different than with RStan ARM, but basically the intercept is given in the first row here and the coefficient on x in the second. This thing called, so one thing about BRMS, and because it's pitched to the psychology audience, it is fully Bayesian, but Paul makes a lot of things to make it look not that different from frequentist output. So we have this column called estimate. Technically, that's average. It is the average of the 4,000 draws. It is not the median, which is the first column in the RStan ARM output, but neither is this like the mode or like the maximum likelihood estimate or whatever, but it's called estimate in order to make it sound frequentist. Est error, that means standard deviation. The lower 95% CI, that is the lower bound of the 95% credible interval, but Paul is trying to make it sound similar to the lower bound of a 95% confidence interval. Similarly with the upper bound, you get an estimate of the R hat, which we saw before. This should be extraordinarily close to 1 if your Markov chains have run long enough. We also get estimates of the bulk effective sample size and the tail effective sample size. This is an additional distinction. that we haven't talked about yet, but we've talked about effective sample size. And so this is sort of effective sample size for estimating quantities that depend heavily on the tail of the distribution, whereas this is an effective sample size for quantities that are sensitive to the middle, which is to say median, of the posterior distribution. Both of these are in the 3000s or whatever, which is plenty, and 4,000 is the nominal value, so this is getting very close to that. There's also a thing called family-specific parameters, family-specific being specific to the normal distribution, aka what's the posterior summary for the sigma parameter, and it has a posterior mean, as well. So the posterior median is not actually shown here, but you could easily calculate it yourself from the draws. So anyway, this is mostly cosmetic differences. It's still taking 4,000 draws. It is entirely Bayesian, but it goes to some length in order to not make it look that Bayesian. Questions about the output?
Might be jumping the gun. Was there a way to see the median?
I just convert this with as matrix or as data frame, and then you get a data frame with 4,000 rows, and then you can do whatever you want.
Oh.
There might be some shortcut to doing that, but it would take me longer to look up the shortcut than it would be to just do what it is I want to do. So an example of one of these shortcut functions is the hypothesis function. So again, this is not a point hypothesis function. This is a substantive hypothesis function. And so to do this in R-stan-arm, you would have to coerce it to a tibble and then see how many of the 4,000 draws are positive or negative. Paul has essentially a convenience function to do this for you. So post as the object on the previous slide produced by BRM, and then you can specify a hypothesis such as the coefficient on X is negative. And then what you get back is basically the posterior probability of the coefficient on X being negative, which in this case is 1, which is also supported by the fact that you get 1 star. And so that only occurs when the posterior probability exceeds 0.95.
Yeah, really went to lengths to make this look frequentist, right?
Yes. Even though fundamentally it's not.
Oh, yeah.
But he really had to fool psychologists into using BRMS. But he's done a really good job of fooling psychologists into using BRMS, and it has, since the plot that I made the first day, BRMS came out after that. So BRMS has legitimately become pretty popular in psychology, particularly in Europe. So in the manner of speaking, he has done a good job of fooling a lot of psychologists into using Bayesian stuff and either not realizing it or not really fully recognizing what it is they're doing. Okay, so I lost my plot. So are there any questions so far while I recompile this?
Could you talk about how psychologists use it specifically, our psychology researchers?
Yeah. So they take the same data that they've been collecting for forever. Experiments they do on undergraduates and things like that. And then, rather than using GLM or SPSS or something like that, Paul has convinced a whole bunch of them to use BRMS. Often with the default priors, which, like I said, you can do a lot better. But You could also do worse by using SPSS. And then they get back the output, and I mean, some of them legitimately do know what's going on. But I think a lot of them look at this output and think, you know, okay, well, SPSS is telling me like the same thing when it makes a 95% CI and whatever like this. And then, you know, BRMS, we haven't seen it yet, but it makes a lot of colorful plots and other things like that. And so they think, oh, this is the greatest thing since sliced bread. Which it is, but not for the reasons they think it is. It's kind of a weird dynamic. Anyway, so one of the things that Bayesians can do is use Pareto smooth importance sampling, leave one out, cross-validation estimator of the expected log predicted density as a diagnostic. So you can call the Lu function on something produced by BRMS, just the same way as with our standard. And if you plot the Pareto K estimates, you would get a warning in this situation saying one of your observations has excessively big estimated Pareto K value, that being quarter 201, starting from 1970, which was the first or the second, can't remember which, quarter of the pandemic. So the fact that the posterior distribution is so sensitive to the first or probably the second quarter, I think, of 2020, invalidates the estimator of the ELPD. It doesn't invalidate necessarily the posterior distribution. So the draws in the posterior distribution are going to be fine. But they are fairly sensitive to this one, in this case, atypical point in history. And so the fact that this is above the red line at 1 invalidates the Pareto smooth importance sampling, leave one out, cross-validation estimator of the ELPD. It doesn't invalidate the draws. It just means in order to estimate the ELPD, we're going to have to do something a little bit different than what we talked about last week. And that's actually fairly easily accomplished by specifying moment match equal true. By default, it's false, which assumes that like none of the observations are overly influential. To relax that assumption, you can do with moment match equal true, which will come up with an alternative estimator of the ELPD, which is less efficient but less sensitive to that assumption. And you can do the same posterior predictive checks that we've been doing. So when possible, you should use the leave one out concept. One thing that trips people up, the PB check function in BRMS, it has different functions, different plots that it can make, but those are indexed by the argument type, whereas RStanArm, it's called plot fun. So there's a lot of things like that with BRMS where there's like small differences between how BRMS does things and how RStanArm does things, like type versus plot fun being the name of the argument. But conceptually speaking, they're doing basically the same thing, but BRMS does more things, or it can estimate more models. And so we get the predictions, and you see, you know, the predictions during the first 2 quarters of the pandemic, not great, not too surprising. Before, I've been just only using the data up to the end of 2019 to not encounter this problem. But if I had used all the data, which I did here, I would notice, I should notice, if I call this and make the plot and see the warning messages, that the posterior distribution is particularly sensitive to this 1 quarter where it's either this one or this one. You know, the economy was just like out of control due to either the lockdown or coming out of the lockdown. Can't remember which. So anyway, you should know if your model is particularly sensitive to what might be considered an outlier quarter in the past 100 years. But if you do the moment match equal true business to do an alternative calculation of that, then it actually comes out to be a pretty good calibration. So this model, aside from the first couple of quarters of the pandemic, is yielding fairly well calibrated predictions of GDO. Okay, so other things that you can do with the methods after estimating something with BRM. Like I said, these are analogous, not always literally the same in how they're called, but they do the same sorts of things that you can do with our stand arm, like launch shiny stand, Loo, make the draws into an array or a matrix or a data frame, things like that. Other things which we'll see later, maybe you can get the stand code, you can get the stand data, you can plot stuff. So most of these are in posterior EPRED, posterior predict, things like that. Those are gonna do the same things as what they do with our stand arm. They just might have slightly different syntax as to how you do them. Did you have a question? No? Okay. So there's like hundreds of things that you can call after producing an object with BRM. Many of those are somewhat useful. So here's an example of a model. Comes up a decent amount of time in social science. You can do this with BRM. You cannot currently do this model with our stand arm. So this is called a categorical logit model on a sample space consisting of the integers between 1 and j, often used for modeling categorical outcomes where there are j. J is not necessarily 2 choices you can make. So a very classic example of this in social science is which brand of orange juice do you buy? So if you go to the grocery store, orange juice section, there are capital J brands of orange juice. Which one do you buy? And the predictors of that might be the price of the orange juice, you know, if it has like hormones or whatever in it. Yeah, like humanely treated oranges. I don't know. Does it have pulp or no pulp or light pulp? Or, you know, the different things that basically differentiate between what is fundamentally orange juice. But people, for whatever reason, have fairly strong preferences about which brand of orange juice they buy. So what would be the math for the generative model behind this? Well, y, which is an integer between 1 and j, is defined as what is the argmax, the value of j, where eta plus epsilon is the highest for person n among the capital J choices of orange juice. The errors are independent of each other and drawn from a standard Gumbel distribution, which we have not talked about yet. But the difference between two independently and identically distributed Gumbel random variables is standard logistic. So if capital J is 2, this is going to simplify to a binary logit model. So it's a generalization of binary logit to the case where there are j possible choices, we have a linear predictor. We can do the usual thing where we actually make alpha be a derived parameter and put the priors on gamma, put the priors on the coefficients. Difference here being we need to put an intercept and coefficients for all capital J brands of orange juice. Or maybe all except the first one, which would be like a reference category. So code to draw the parameters might look like this. We've seen per before. Basically, I'm saying just do this for all. If J was 3, do this for all 3 brands of orange juice or whatever that is under consideration. You might see here I've made the first value of the standard deviation be 0. This is for identification purposes. So for the first brand of orange juice, I'm going to force all the betas to be 0, and then estimate the coefficients for the x's, whatever the x's are, for the other brands of orange juice relative to the reference brand of orange juice. So that's the reason why if we have 3 brands of orange juice, I'm going to get back 3,000 draws, so maybe 1,000. But anyway, you get the idea. And then to make predictions, cross-join together the priors and the data. Then we're going to group by each of the J brands of orange juice, make a linear predictor, and also some other stuff to keep track of things. And then we're going to ungroup with groups of drop. And then after we've made eta, we draw epsilon. So this formula is how to draw from a standard Gumbel distribution. And then for every N and R indexing the draws for the 3 different types of orange juice. We're going to define Y as the index which maximizes eta plus epsilon, which is what we said on the previous slide here. And then ungroup the whole thing. We get back draws from the prior predictive distribution. And it turns out that the probability of Y being the jth brand of orange juice is going to be e to the eta j divided by the sum of the e to the etas for all the brands of orange juice. And so the log likelihood is just going to be that, the logarithm of that, and then summed over all possible people and all possible brands of orange juice with an indicator function that is 1 if and only if person N buys that brand of orange juice. So anyway, this is called a categorical model. Supervised learning refers to this as multinomial model. So basically, supervised learning reverses the agreed upon for decades in statistics. So what statistics calls categorical, supervised learning calls multinomial, and what supervised learning calls categorical, statisticians call multinomial. But in any event, multinomial is similar to binomial in that it's the sum of a whole bunch of categoricals with the same probability. It's just binomial is specifically for the case of 2, multinomial for the case of J, where J could be 2 or not. So to show an example of how this is used, we're going to do something that is not social science, but rather use a data set that comes with R called iris. So iris is a type of plant, and this data set is used all the time with like classification examples and stuff like that. Basically, the goal here is to predict the species of the plant, of which there's 3 possible iris plants, based on characteristics of the sepal and the petal. So sepal, I think, is like the neck of the plant, and then petal for the leaves. Oh, and there's 3 different types of iris: setosa, versicolor, and virginica. So anyway, we're going to specify standard normal priors on the coefficient of sepal length, sepal width, petal width for the different ones. In a categorical model, we also have to specify dpar to indicate which part of the model our priors are pertaining to. So this is for like mu of the versicolor part of the model, and this is for mu of the virginica part of the model. By default, it's going to make all the coefficients for the setosa part of the model 0 for identification purposes, and then estimate the betas of everything else relative to that. So what we should do is check whether these priors yield reasonable predictions, and that can be done fairly easily in BRMS, just the same, almost the same as in RStanArm. So we specify a formula where the variables are categorical likelihood, prior is my prior, which I constructed here. If in BRMS you do sample underscore prior is only, then it's not going to condition on the outcome data. It's only going to draw from the priors, and then you can make posterior predictions, which are actually prior predictions, or you can make the plots, all that sort of stuff, to see if your priors imply a reasonable prior predictive distribution, and then if so, you can go ahead and condition on the data. So then when we call update, and then instead of sample prior equal only, sample prior no, which is the default, that means condition on the data, give me draws from the posterior distribution, and that's what we get back. And then you can make the plots correspond to that. So this is similar to plots that we've seen before. It's just now we have coefficients that are indexed by what species of iris it is. So we have the versicolor and the virginica here. The coefficients on sepal length and sepal width and whatever they have. Those distributions, which are typically not so far away from 0. And then we also have intercepts, which are not particularly precisely estimated. But in any event, like a lot of these GLMs, this is in the units of eta, which are not even interpretable as log odds, like they would in a, if this was a binary logit model, this could be interpreted in units of log odds, but this has 3 categories, not 2, so it's even less interpretable than that. So one thing you might want to do, or you should want to do, is show how the posterior expectation varies as a function of, something. So for that, we can call posterior EPRED, like we did before. So that's going to return me 4,000, which is the number of draws, by 150, which is the number of observations, by 3, because there's 3 types of iris, array of expectations, which in this case are probabilities. So they're going to sum to 1 across the 3 shells of this array. I can also call posterior underscore predict, which is going to give me a 4,000 by 150 predictions, and those are going to be integers, 1, 2, or 3, depending on whether it's predicting for that posterior draw that the nth thing is either setosa or virginica or the other one. So anyway, you can make plots like this one that I'm going to show here. So on the horizontal here, we have mu, the expectation or the probability that the plant is this or that species. And so for setosa, there are a lot of observations that have pretty much 0 probability of being setosa, given their neck and their leaves. And there are not as many, but there are also a lot that have like a 0.9 probability of being setosa. So I don't know the details of it, but basically with the petals and the sepals, just knowing that information alone pretty much definitively tells you whether it is setosa or not. It's not as stark with the versicolors. So there's a bunch, not as many, but a lot that have like a 0.1 probability of being versicolor. And then there's some, but not all that much, that have like a 2/3 probability of being versicolor. So the petals and the sepals are like not totally sufficient information for saying whether the plant is versicolor. And with virginicas, there's a lot of them that we can rule out it being virginica based on the sepal and the petal. But the probability that it actually is a virginica is pretty uniform. So it's harder to distinguish versicolors from virginicas based on the 2 or 4 whatever predictors that we have. You might need to know more information to classify those as well as we do setosis. But you can certainly make the plot. Questions about what I've done here? All right. So another model that we just barely have time to get into is a survival model. So these are very common in public health, or they're common in public health, and survival models also often have censoring. So in public health, the main thing that gets modeled is the amount of time until someone dies. But in the data sets they collect, some of the people are not dead yet at the time the study runs out of money. And so we know they lived up until we stopped paying attention, but we don't know how long it is they lived after that. They might even still be alive, but they're going to die eventually. We're just not observing in this data set the time at which they die. And so generative model for a situation like that, y, the amount of time we observe, it's equal to y star if y star is less than the censoring time. So let's say our study is going to be like a year long. C would be 365 days, or 1 year, or 12 months, whatever the units want to be. Okay, if we observe the person dies after 10 months, then this is going to be 10 or whatever. But if they live longer than a year and our study is only specified to run for a year, then what we observe in the data is that they lived for at least a year if the amount they live is greater than the study duration. So, okay, if that's how yn is related to y star, how is y star generated? Well, we can assume, among other things, that it's an exponential distribution with a rate of 1 over mu. Okay, what's mu? Mu is e to the eta. Okay, what's eta? Eta is a linear predictor thing. Involves coefficients, gamma, beta, whatever. Those can have normal priors similar to, what we've been doing. Main thing here is C is known. You should know when your study ends or when someone else's study ends. That shouldn't be a random variable that you have to estimate, although theoretically you could do that. We're not doing it in this case. So, example code to draw from this generative process, start at the bottom, go to the top, make gamma and beta your priors, cross-join it with the data, make eta. Let's assume x has already been centered. Mu is e to the eta. Y star is a draw from the exponential distribution with expectation mu, or rate reciprocal of mu. And then if y star is greater than c, return c. If y star is less than c, return y star. Make that into y. And now we have predictions for observed y. We can see if those are reasonable before proceeding. So in these survival models, okay, if it's less than C, we observe the survival time exactly. If it's equal to C, that means we don't observe the survival time exactly, we observe a lower bound. So how does the likelihood function or the log likelihood function work? Well, if we observe Y exactly, then it's just the log of the distribution, in this case exponential, it could have been something else, whose parameters are given by eta. But if the person lives longer than C, then the contribution to the log likelihood is the log of 1 minus the CDF evaluated at C. So the CDF is the probability the person lives less than or equal to C. So 1 minus the CDF evaluated at C is the probability that they live longer than C, which is what happens in this scenario. And then the logarithm thereof is what goes into the log likelihood. So honestly, it's more common to use other distributions than exponential, such as Weibull, but it would be, similar data generating process. So that just swap out a different distribution. So as an example of doing a survival model, what is BRMS? It comes with a data set of people who have, I think, fairly severe kidney disease. So this is the first few observations of that. So we have the time. I'm not sure if this is the time until like actual death, or this might be like time until they had to go to the hospital or something like that. We have an indicator as to whether this is a censored observation or not. These first bunch are not, but the last many are. We have an indicator for who the patient is, their age, whether they're male or female, and what sort of kidney disease they have. So anyway, we can specify prior in the sort of usual BRMS way on the intercept and use a standard normal prior for all of the coefficients. So if you just do class equal B without any further specification, it's going to be using this standard normal prior for all of the coefficients. But that's certainly better than using an improper prior for all the coefficients. So the way in which this would get done in BRM, you specify your outcome variable, time. Like I say, I don't think this is actually time till death. It's like time till something not quite as bad as death happens. But this is a situation where we have to use the special syntax. So this doesn't mean or, and it doesn't mean given. It just means separate. And then we're saying our censoring indicator is the sense variable. We're going to model this as a function of the interaction between age and sex, and then have a disease, which is a factor variable, so this is going to become W variables as to what kidney disease the person has. That's where the variables are, exponential likelihood, and then prior is this. Okay. It compiles, it runs, we get back numerical summaries of this, effective sample size, still looking good. It's not quite as high as it was on the other model, but plenty with which to estimate precisely pretty much anything we would want. Because age, we didn't change the units, so I usually make age in decades, but I forgot to with this, and that's why we get like to 2 decimal place. The effective age is 0, which is to say the expected difference between 2 people who differ by 1 year is maybe not nothing, but it is pretty close to 0. That's why I usually change age to be in decades. But female are likely to have longer times than men. None of this is very precisely estimated, but anyway it is. So as usual, this is going to be in units of eta. We might want to make a plot to say how the expectation of time changes as a function of, these are the variables. And so we have age here, and we facet it by sex and facet it by disease. As it turns out, it doesn't seem like age has that much of an effect because these lines seem to be fairly flat. But this is an example of how we can make plots by making queries to the model. All right, so out of time, I will post another homework either tonight or tomorrow morning. It will use brms, so make sure your C++ toolchain is set up. It'll be as usual do before class next time. And then next time we'll start talking about models for ordinal outcomes. This is something very important in political science and in particular psychology. So brms has a lot of good functionality for those sorts of models. Also, for models that have ordinal predictors, we can do some cool stuff with that. So anyway, as usual, we'll have office hours and recitation next week. But anyway, if you have questions, you can certainly ask about them on Ed Discussion, and particularly if you have questions about how to set up the C++ thing.
It says,